Good morning, dear students. Let us derive expressions for time domain specifications in today's class. Expressions for time domain specifications. First, let us take up rise time TR. So the unit step response of second order system for underdamped case is given by the unit step response of second order system for underdamped case is given by C of t equals 1 minus e power minus zeta omega n t divided by square root of 1 minus zeta square into sine omega dt plus theta. So this we have seen in the last class, that is the response of a second order system for an underdamped condition. We have derived this equation in the last class. We will start from this point. Okay. So at time t is equal to tr, what is the response? Response will be equal to 1. Okay. That is what the definition of rise time for underdamped condition which we have discussed in the last class. That is at rise time tr, output response will be equal to the applied input. Applied input is a unit step. So we found that output response at C of TR will be equal to 1. Okay. So now I'll be writing at C of TR, which is equal to 1, which is equal to 1 minus e power zeta omega n TR divided by square root of 1 minus zeta square sine omega dtr plus theta. What I did? I just took the equation. In this equation, I substituted T as TR and I equated the whole equation to 1, because we know that at rise time, the response will be equal to 1. Okay. So therefore, we can simplify this to be minus e power zeta omega n TR divided by, this is minus 1 minus zeta square sine omega dtr plus theta equals 0. What I did? I have just sent this one to the left side and get cancelled. So I have only this term, that is minus e power minus zeta omega t minus zeta omega ntr divided by square root of 1 minus zeta square sine omega dtr plus theta. Okay, we got only this term and I am equating that to 0 now. That's what the left hand side had become 0. So I have this term becoming 0. Okay, so now we know that e power minus zeta omega ntr cannot be 0, correct? Since time tr is not 0, this term cannot become 0. So then I can say that the term sine omega dtr plus theta has to be 0, correct? Because this term cannot be 0. So this has to be 0 now, so as to match this condition. Okay. So now we know that at phi equals 0, pi, 2 pi, 3 pi, so on, then sine phi equals 0. We know that sine and pi is equal to 0, so that I can say that omega dr plus theta equals phi. Okay, so when this term should be equal to 0, then this angle has to be pi. Okay, so we have here omega dtr plus theta equals pi. So omega dtr equals pi minus theta. This is what we can write. So I can write that rise time Tr is equal to pi minus theta by omega d. I can write like this. Okay. I can substitute this omega d. Okay. What is omega d? Omega d is equal to omega n into, omega d is equal to omega n into square root of 1 minus zeta square. This we know. Okay. So this is about the rise time. Okay. So next we will take up the peak time. So what is a peak time? Peak time is a time instant at which our output will be maximum. Okay, maximum possible. So this is what we have, peak time TP. Okay, so this is the time corresponding to the maximum output. Let us derive a condition for this, the equation for this. I'll go to the next sheet. Okay, so let us derive an equation for TP now. Okay, so to find an expression for TP, what we do, how do we find the maximum and minimum of a function? We differentiate that function with respect to time and we will be equating to 0. Okay, so that's what we will be doing here to find the expression for peak time TP. Differentiate C of t with respect to t and equal to 0. That is, we have d by dt of C of t at t is equal to dp equals 0. So this is what we have. So we found that at peak time, we found that the signal derivative will be 0. So we are using that condition to find an expression for TP. Okay. The unit step response of underdamped condition is given by the unit step response of underdamped second order system is given by C of t equals 1 minus e power minus zeta omega n t divided by square root of 1 minus zeta square sine omega d t plus theta. This is what the equation we derived in the last class for C of t, that is the response of second order system for the unit step input. Okay. So now we have to differentiate this. So differentiate C of t with respect to t. Okay, with respect to t. So d by dt of Ct is equal to, so what we have, the first term is a constant. If I differentiate that constant, it will be 0. Okay, first term will be 0. So I have the second term, which is a product of two function. So what I do is differential of first into second plus first into differential of the second. That is the formula I'll be using it. I repeat what I'll be doing. I'll just take this product of two function now, the second term. So if I differentiate this product of two function, then what I do is first differentiate first, keep the second as it is, plus keep the first as it is and differentiate the second. Okay, so that's what we are doing. I'll be differentiating the first function, which is e power minus zeta omega n t divided by square root of 1 minus zeta square into minus zeta omega n. Okay, into sine omega dt plus theta. Okay, what I did, I differentiated the first term and I have kept the second term as it is. Okay, second term as it is, I will keep it. So now what I do is I'll keep the first one as it is. I'll keep the first one as it is and I differentiate the second term. Okay, keep the first one as it is, differentiate the second term. So what is the second term? What is the second term? It is sine omega dt plus theta. If I differentiate that, I will be getting cos omega dt plus theta. And omega dt, if I further differentiate, I will be getting omega d. Okay, so this is what I'll be getting. Now put omega d as what? Omega d as omega n square root of 1 minus zeta square. Then I can write it as d by dt of this c of t expression, which is equal to e power zeta omega n t divided by square root of 1 minus zeta square zeta omega n sin omega d t plus theta minus e power omega n square root of 1 minus zeta square divided by square root of 1 minus zeta square e power minus zeta omega n t into cos omega dt plus theta. Okay, so what I did, I have just I have just substituted for omega d as omega n square root of 1 minus zeta square. Okay, so that's what I have done it here. So this minus minus, it becomes plus, and I'll be having this expression here. Okay, so this is what I'll be getting it. Okay, so now what I'll be doing is I'll further simplify this. I'll just group the term. I'll just group the term. So I can write it as d by dt of c of t, d by dt of c of t, which is equal to, I'll take omega n square root of 1 minus zeta square. I'll take omega n e power, very sorry, I will erase this for so what I do is I'll take omega n e power minus zeta omega n t, I take it as common, divided by 1 minus zeta square. Then what are the terms left out? It is zeta sine omega dt plus theta minus square root of 1 minus zeta square into cos omega dt plus theta. This is what I will get. Correct? Am I correct? I repeat. What I'll be getting? I'll be taking here omega n e power minus zeta omega n t as common. I'll take it out, divided by square root of 1 minus zeta square. So what are the terms left out now? Zeta sine omega dt plus theta minus square root of 1 minus zeta square cos omega dt plus theta. So this is what I'll be getting. Okay. So now what I do is I will just use the right angle relationship. I will be using the right angle relationship which exists between the zeta and square root of 1 minus zeta square, and I will be rewriting the expression. What is this right angle relationship which we have discussed in the last class? If this is theta, then this is 1 minus zeta square, this is zeta, and this is 1. Okay, so cos theta I can write it as zeta, and sin theta I can write it as square root of 1 minus zeta square. So this is what the relationship exists between zeta and theta. So this is what we can write it. So extending this relation to the c of t expression, I can write it as omega n divided by square root of 1 minus zeta square e power minus zeta omega n t multiplied by cos theta sin omega dt plus theta minus sin theta cos omega dt plus theta. I can write like this. So what I did, just go to the previous sheet, you will get to know what I did. I have just taken theta in place, sorry, in place of zeta, I have taken cos theta. In place of square root of minus zeta square, I have taken sin theta. So that's how I have done it. So I got this equation. Okay. So now I can simplify this as omega n divided by square root of 1 minus zeta square e power minus zeta omega nt multiplied by sine omega dt plus theta into cos theta. Just I'm doing the term adjustment so that you can compare this to a sine a minus b formula. Okay. So this is what the term adjustment I did, and I can just directly write this as sine. This particular thing will become sine A minus B formula. So I will be using that, and I can write it as sine omega dt plus theta minus theta. Okay, this is what I'll be getting. Okay, so this is equal to omega n divided by square root of 1 minus zeta square e power minus zeta omega n t sine omega dt, because theta get cancelled. This is what you will be getting. Okay, and we know that at t is equal to tp, that is at peak time, derivative of that response will be 0, correct? Reaching maximum, function is becoming maximum. Therefore, omega n divided by 1 minus zeta square e power minus zeta omega nt sine omega dtp equals 0, correct? We know that e power zeta omega n tp cannot become 0 because tp is positive, it cannot be 0. Then sine omega dtp has to be 0. And we know that for phi equals 0, pi, 2 pi, 3 pi, so on, sine phi is equal to 0. We know that. So that I can say that omega dtp is equal to pi. Okay, omega dtp is equal to pi. So that I can write peak time as Tp equals pi by omega d. I can write like this. Okay. So, and we know that omega d is equal to omega n square root of 1 minus zeta square. Okay. So that I can write Tp as pi divided by omega n square root of 1 minus zeta square. I can always use this equation also. Okay, so this is about the time tp. Okay, so next we will go to the peak overshoot. Okay, I'll go with the peak overshoot expression. So peak overshoot derivation we are doing, we call it as mp. Okay, this is mp derived. We have to derive an expression for this. So what is the formula here for the peak overshoot? The peak overshoot is defined as percent MP, which is equal to C of Tp minus C of infinity divided by C of infinity into 100. This is according to the time domain specification definition. We have percentage overshoot given by this equation. Okay. So here, what is C of Tp? C of Tp is the peak response, at t is equal to t. Okay. At t is equal to infinity, what do we call it as? Final steady state value. Okay. Now, for the unit response, for the unit response of second order system is given by C of t is equal to 1 minus e power minus zeta omega n t divided by square root of 1 minus zeta square sine omega dt plus theta. Okay. So we know that at t is equal to infinity, C of t is equal to C of infinity is equal to 1. Okay, we know that at steady state it will be approaching the input which is equal to 1. Okay, and we know that at t is equal to Tp, C of t is equal to C of Tp, which is equal to 1 minus e power minus zeta omega n Tp divided by square root of 1 minus zeta square sine omega d Tp plus theta. Okay, this is what the output at the peak time. Okay, so now I know that at Tp is equal to pi by omega d. Just we have derived. Just now we have derived this. Okay, so now I will be substituting that. So I get an equation e power minus zeta omega n pi by omega d divided by square root of 1 minus zeta square sine omega d pi by omega d plus theta. So this is what I'll be getting. Okay. So now what I do is I substitute for omega d. Okay. If I substitute for omega d, what I'll be getting? So zeta omega n into pi divided by omega n square root of 1 minus zeta square sine pi plus theta, because omega d here get cancelled. So pi plus theta I'll be having, in the denominator I'll be having 1 minus zeta square. So this can be further simplified as minus and minus, I will make it plus here. So it is e power minus zeta omega n pi divided by omega n will get cancelled, very sorry, omega n will not be there. Zeta pi divided by square root of 1 minus zeta square divided by square root of 1 minus zeta square sine theta. Okay, this is what I'll be getting. Since omega d is equal to omega n into square root of 1 minus zeta square and sine pi minus plus theta is minus sine theta. Okay, we have used this relation and we could write this expression. So what we did, we have substituted omega d as omega n square root of 1 minus zeta square. This omega n cancels. So I'll have a term here e power minus zeta pi divided by square root of 1 minus zeta square multiplied by sine theta. Why? Sine pi plus theta is minus sine theta. So that minus I took it here and I got sine theta simply here. Okay. So now I use the right angle relation again. So right angle relation, what we found it as sine theta is equal to this is zeta, this is 1, this is square root of 1 minus zeta square. So I have sine theta as what? I have it as square root of 1 minus zeta square. Okay, I know this relation. So now what I do is C of Pp, I'll be substituting that value which is equal to 1 minus e power minus zeta pi square root of 1 minus zeta square divided by 1 minus zeta square. For sine theta, I'll be substituting. For this sine theta, I'll be substituting this, which is equal to 1 minus zeta square. So this and this get cancelled now. So I'll be having the C of Tp as what? C of Tp as 1 plus e power minus zeta pi divided by 1 minus zeta square. Okay. So now what I do is I just go to the definition and I substitute this. Okay. So C of Tp, I have the value. Okay. So here I have written the definition. To this definition, I'll be substituting C of T and C of infinity. Okay. So let us do that. Okay. So I'll be substituting in this percentage peak overshoot. peak overshoot, which is percent MP, it is equal to C of Tp minus C of infinity divided by C of infinity, okay, multiplied by 100, correct? This is what the, according to the definition, we have this equation. So I'll be substituting now for C of Tp. So C of Tp, what I have, it is 1 plus e power minus zeta pi divided by square root of 1 minus zeta square. And what is C of infinity? It is equal to 1. And in the denominator, we have 1. So this is what we'll be getting. So this and this get cancelled. So I'll be having now percentage MP as equal to e power minus zeta pi divided by square root of 1 minus zeta square into 100. So this is what the equation for peak overshoot. Okay, this is what we can write. Okay, so next we have to derive an expression for settling time. Time, settling time, we have to write the equation which is equal to Ts. Okay, it is settling time Ts. The response of second order system has got two components. Okay, the response of second order system has two components, correct? What are those two components? They are, one is the decaying exponential component. So decaying exponential component, it is e power minus zeta omega nt divided by square root of 1 minus zeta square. And the second one is sinusoidal. Second one is the sinusoidal component, sine omega dt plus theta. Okay, so we have these two components which contributes the output C of the expression. Okay, so in this decaying exponential term reduces the oscillation produced by the sinusoidal component. Hence, the settling time is decided by the exponential component only. The settling time can be found out by equating exponential component to the percentage tolerance error. Okay. So if you want a 2% tolerance error band, then T is equal to Ts. Okay. Then we will be equating that to exponential component, you have to equate to 0.02. Okay. So let us write this point. Okay. So in this, the decaying exponential term reduces the oscillations produced by sinusoidal components. Hence, the settling time is decided by the exponential component only. The settling time can be found out settling time can be found out by equating exponential component to percentage tolerance errors. Okay, so what we can say now, what percentage of tolerance we want, based on that we will get the expression. Okay, so now I'll go with the 2% tolerance. Okay, for 2% tolerance error band at t equals ts. Okay, I'll be equating this exponential term to 0.02. Okay, so now for the least values of zeta, so zeta, e power minus zeta omega and ts will be equal to 0.02. Okay, so we have assumed that zeta is very, very small. Okay, so we have to take natural log on both the sides, because we want a expression for ts. Take a natural logarithm on both the sides, we get minus zeta omega and ts as the natural log of 0.02. This implies minus zeta omega and ts will be equal to -4. So this implies ts is equal to 4 divided by zeta omega n. So what we did? So we have taken only the exponential term, which is contributing for the second time here, and we have assumed zeta to be very, very small. So we found that e power minus zeta omega and ts to be the 2% tolerance which we are looking for. Taking natural log on both the side, we will get ts as 4 divided by zeta omega n. Okay, so this is what we have for the 2% error. Okay, for the 2% error. So similarly, we can do it for 5% error. Okay, so for 5% error, for a 5% error, e power minus zeta omega and ts should be equal to 0.05. Okay, taking natural log on both sides, I'll be getting zeta omega and ts as natural log of 0.05, which implies minus zeta omega and ts as -3. So t is found to be 3 divided by zeta omega n. Okay, this is for the 5% error. Okay, so settling time for 5%. Okay, so in general, for a specified percentage error, settling time can be evaluated using the equation ts is equal to natural log of percentage error divided by zeta omega n. Okay, so this is what the generalized settling time expression. Okay, so this is about the what we call it as the time domain specification expression we have derived for all the specification. Okay, so I would like to stop here. I'll continue with this in the next class. Okay, thank you.